Imagine a world without transistors. It's like a city without traffic lights. Chaos, isn't it? Picture this. Every device you own, from your smartphone to your microwave, relies on these tiny yet essential components known as transistors. At their core, transistors are the traffic lights of the electronic world, regulating the flow of electricity, much like how traffic signals guide vehicles. Transistors are born from a fascinating dance between science and technology, a dance that starts with a simple piece of semiconductor silicon. Through a process known as p-type doping, the silicon is transformed into a PNP transistor, a device that can control the flow of electricity, or more accurately, the flow of electrons. One of the key characteristics of a transistor is its current gain, a property that allows it to amplify or switch electronic signals. Imagine a river of electrons flowing through a transistor, guided and controlled by the invisible hand of technology. So, without transistors, our modern world would be in a state of technological chaos. To understand transistors, we need to understand the flow of electrons. Think of electrons as dancers moving to the rhythm of energy. Imagine a grand ballroom filled with dancers. Each dancer represents an electron. The music that guides their movements is the energy that propels these electrons. Just as dancers move across the floor, electrons move from a region of high energy to a region of low energy. This movement is what we refer to as electron flow. Now let's take a closer look at our dancers. They're not just aimlessly wandering around. They're actually following a very particular pattern, a choreographed dance, if you will. This dance is determined by the properties of the material they inhabit and the energy supplied to that material. Consider a semiconductor like silicon, the floor of our grand ballroom. It's a special kind of dance floor, one that allows the dancers to move, but not too freely. This is because silicon atoms form a tightly packed lattice through a process known as covalent bonding. However, we can change the nature of this dance floor by introducing impurities, a process called doping. For instance, when we add a bit of phosphorus to our silicon, we create an N-type semiconductor. This introduces extra dancers or electrons, making the dance floor a bit more crowded. But what happens when we add boron instead? This creates a P-type semiconductor, where we essentially have holes, or spaces on the dance floor. These holes are positively charged, and are eager to be filled by our electron dancers. When we place an N-type and P-type semiconductor together, we create a region in the middle called the depletion region, where no dancers, or rather electrons, want to go. It's like an invisible wall in the middle of the dance floor. But when we apply a forward bias, or turn up the music, the electrons overcome this barrier and the dance continues. So, in a nutshell, the dance of electrons is what powers our electronic devices. Now, let's dive deeper into the world of atoms and explore the magic of covalent bonding. Imagine attending a grand party where everyone is eager to dance. In this ballroom of atoms, everyone has a partner, and they're all in a constant rhythmic swing. This dance is what we call covalent bonding. Just as two dancers hold hands, two atoms share a pair of electrons, creating a bond that's as strong as a firm handshake. Picture two people meeting for the first time at this party. Let's call them silicon and silicon. They're identical twins, each with 4 valence electrons. But to be truly stable, they need 8. So what do? They form a pact. Each silicon shares its 4 electrons with the other, creating a bond where both feel complete. This mutual sharing and holding of electrons is the essence of covalent bonding. But what happens when a silicon atom meets someone new at the party, like phosphorus? Phosphorus is a bit of a show-off with 5 electrons to share. Silicon, remembering its pact, can only accept 4. This leaves phosphorus with an extra electron. This small change disrupts the balance and creates a positive charge, leading to what we call P-type doping. However, this isn't a disaster. In fact, it's quite the opposite. This imbalance creates a unique region called the depletion region. It's like a wall at our dance party that dancers must cross to switch partners. This wall can be manipulated with a little encouragement, or what we call forward bias. This allows the electrons to move, creating the flow that's the lifeblood of our transistors. So, just like dancers at a ball, atoms in a semiconductor silicon engage in a delicate dance of covalent bonding. This dance isn't just for show. It's the fundamental principle that allows us to harness the power of electrons and create the technology that powers our world. So covalent bonding is the handshake that allows electrons to move and power our devices. Now that we understand how transistors work, let's explore their impact on our everyday life. Imagine a world without computers, smartphones, or even space technology. Sounds like a page from an ancient history book, doesn't it? Well, that's the world we would be living in without transistors. These tiny components are the heartbeat of modern electronics, making them an integral part of our everyday life. Let's take a closer look at the magic of transistors. Consider your smartphone. It's a device you probably can't imagine your life without. It's your alarm clock, your personal assistant, your entertainment hub, and so much more. But have you ever wondered what makes your phone so smart? The answer lies in millions of transistors. These transistors, acting as electronic switches, control how electricity flows through the circuits of your phone, enabling it to perform complex tasks at lightning speed. Similarly, in computers, transistors form the foundation of microprocessors, the brain of the computer. They control the flow of information, allowing your computer to process data, run software, and connect to the internet. In fact, a single microprocessor can contain billions of transistors, each one contributing to the overall performance of the system. Now let's take our gaze upwards, into the vast expanse of space. Space technology too relies heavily on transistors. From guiding spacecraft to distant planets to receiving signals from far-off galaxies, transistors play a pivotal role in helping us explore the final frontier. So, whether it's sending a text message, streaming a movie, coding a software, or even launching a satellite, transistors are the unsung heroes behind the scenes, making it all possible. They've revolutionized the way we live, work, and play, transforming our world in ways we could have only dreamed of a few decades ago. Without transistors, our modern world would be a much different place. So the next time you pick up your phone or sit down at your computer, remember to give a silent nod to the humble transistor. As we look towards the future, the role of transistors in our life is set to become even more crucial. Transistors, these silent heroes of our electronic age, are not standing still. They're evolving, getting smaller, faster, and more efficient. Researchers are ceaselessly pushing the envelope, exploring the limits of materials, and discovering new ways to amplify their potential. Take, for instance, the advent of quantum transistors, a new frontier that promises to revolutionize computing. Or consider the rise of biocompatible transistors, which could one day deliver personalized medicine straight to our cells. Then there's carbon nanotube transistors, which are expected to outperform silicon-based ones, ushering in a new era of speed and efficiency. These advancements are not just about making things smaller or faster. They're about transforming how we live, work, and play. As we continue to push the boundaries of technology, the humble transistor will remain at the heart of our electronic revolution.